Morning everybody. Today we're going to look at binary logic. We're going to start with the first of two lessons. So as you can see, binary logic, two lessons, on slide two lessons. So the first lesson today is on computational thinking and logic, and then truth tables. And then next week we will look at logic gates and their own specific truth tables, and we will look at simple logic circuits. So slide 3. Lessons learning objectives are 1. To understand what we mean by logic. Number 2, to understand what we mean by binary logic. Number 3, to understand what we mean by computational thinking. And finally, number 4, to be able to create and complete truth tables. So, what is binary logic? Computers use binary logic to do a great many things. Binary logic is where we say if something is either true or false. There's no maybes, there's no kind of, it's just true or false. Or if you remember when we were doing binary numbers, we looked at it and we kind of worded it as, a switch being on or off, because the reason is the transistors inside the CPU only understand on or off states. They can't be, maybe off, maybe a bit on, partially open. It's just on or off. So, like example, this is a car. It's either true or it's false. It's either a car or it's not. So, is it predictable? Binary logic must be predictable. Now, this means that if we ask something over and over again of a computer, you'll always get the same answer, whether it's true or false. It's a part of the challenge of programming is understanding or being able to predict the outcome that we want. Computers are also classed as what's called deterministic. That means their behaviour must be predictable given the same input and circumstances. So, for example, when you press the power button, the operating system is going to come on. When you double click on the Word icon, it's going to open Microsoft Word. Or, when the device is booting up, it's going to check to see if there's certain hardware in place in order to carry on booting up the operating system. So far we've looked at two learning objectives. What do we mean by logic and what do we mean by binary logic? Moving on then to computational thinking. That is, it's a thinking that allows us to take a complex problem and then we develop possible solutions. So as you can see in the little picture, you've got decomposition, pattern recognition, and then algorithmic design. So decomposition is breaking it down into smaller chunks. So if you'd like, rather than saying, let's say, looking at the recipe for a whole meal, you'd look at the individual recipe for making a roast chicken. You'd look at the individual recipe for doing roast potatoes. You break it down into individual recipes to make it easy to understand. And then when you're doing the algorithm, you can do it in steps then. And pattern recognition is looking for things that are repeated more than once, so you can save time by making a loop, for example. So we're going to go through a number of logic examples just to give you some, an idea of what they look like, and then I'm going to ask you to do some work. So logic example 1. 2 statements. Number 1, some students like to travel on trains. Number 2, not all students like cheese. So then which of the following statements are true based on the statement above? I'm not going to read them out, I'll let you read them in your own time. So the answer to logic example 1 is D. Students who do not like cheese may still like the train. Logic example number 2. This time we have 3 statements. Number 1, all teachers like eating burgers. I know in my case that's definitely true. Number 2, only students like eating cheese. That's not true in my case, but that's in this one. And then number 3, students are not teachers. So which of the following statements is true or are true based on the statements above? The answer to logic example number 2 is C. Because teachers are not students, they must not like cheese. The final logic example, remember this is a video, so you can pause it and look at the screen. You can rewind it, listen to it again, anytime you want. Logic example 3. 3 statements again. Bob's car has a top speed of 30, I'm presuming it's miles an hour. Number 2, the minimum speed on the motorway is 40 miles an hour. I think that's true actually. And number 3, cars whose top speed is 30 are always painted blue. So which of the following statements are true based on the statements above? So the answer to logic example 3. A is true, because Bob's car has a top speed of 30. So that also lines up with number 3, cars whose top speed is 30 are always painted blue. And D, there will be no car on the motorway painted blue because the car Any car painted blue has a top speed of 30 miles an hour and therefore is too slow to go on a motorway. So far now we've covered learning objectives 1, 2 and 3. We've done what we mean by logic, we've done what is binary logic, and we have looked at computational thinking. The last thing we're going to look at today is possibly the hardest thing. It's something called a truth table. So binary operators. We can connect statements together by using keywords. We call these binary or Boolean operators. These words are and, or not. Well, truth table for and. Any statement using an and must have two inputs, because you can't have, it's 1 and 2, or input 1 and input 2. Both inputs must be true for an and statement to be true, otherwise it's false. So A being true and B being true means A and B are true, but the rest of them are all false because one of them has one or more false statement in it. Again, pause this if you want to make a bit more sense. If you want to have a look on stuff like BBC Bite Size for maybe a different way of explaining it, or look up your own videos on YouTube and stuff, feel free. Or statements. So this time, both inputs must be false for it to be totally false, otherwise it's going to be true. So you just need one true statement to be true overall, otherwise the only one that's false is the last one, which is false or false equals false. I know it's a bit confusing, but if you read through it, it does kind of make sense. And the final one is not, which is kind of like the opposite, so they literally just swap places. So, something for you guys to have a go at. I will put this slide, you'll be able to copy it off here, I think. Complete the truth table for B and A, not B and then B or A. And an extension task, not A and B. Do you need more columns? Have a think about the brackets. Like I say, have a look back, watch the video again if you want. Feel free to have a look at BBC Bite Size. It is probably the best place to look at these sort of things for another fairly simple way of explaining it. And this is your activity. I'd like you to submit it, either do a Word document or Excel, whatever, or do it on pen and paper, whichever you find easiest. And just to recap then, the learning objectives were to understand what we mean by logic, to understand what we mean by binary logic, to understand what we mean by computational thinking, and finally to be able to create and complete truth tables. That's what I expect you guys to submit by next Monday, please, and take care.